Good afternoon. I'm going to begin with, or going to continue with the inference notes unless you have some questions for me. Remember, the quiz at 6 o'clock is regarding the SDS unit. So do you have any specific questions for me? Sorry, I'm coming on screen now. Hang on. Any minute now. There you go. A little bit blurry. There you go. Okay, so unless you have questions, I'm going to continue with the formula sheet. No, I'm going to continue by answering the question I left you with a few days ago. Okay, so this was the question. The question was for this problem regarding the sampling distribution, the sample size that we should use to estimate the number of Canadians who actually understood the Constitution. So what kind of sample should we use? What size of sample? When we use our formula, which I derived for you the other day so you know where it comes from. And we arrived at this answer, that it should be exactly 9,604. And with that, we chose the option among the alternatives of about 10,000, correct? I erased this though. About 10,000, so that was the best answer. And then I proposed, well, what if maybe I didn't say it. What if you had to choose between these two alternatives? Which is the right answer? Do we round up? Or let's say, let me say this. Let me say, if you have to choose between these two, should I round down or round up? It seems like it's closer, so this is not a very good alternative. Let's make this, I'm going to change this to between, and then I'll explain why after. So choose between 9600 and 9610. So let's say those are the only options you have. Which one should you pick? Any takers? Should I round down or up? What should I be thinking about it? Is it a mathematical rounding? Mathematically, I should just go, that's closer, right? 9600 is closer than 9610. Now, when I asked the original question, 10,000 was the closest, and it was rounding up. So we chose it. We never entertained the idea of 5,000, right? Because that was so far away. But now we have between 9600 and 9610. So what should we be thinking about? Is it obviously one or the other? Well, if you think about where this formula comes from, right? It comes from the margin of error. The margin of error is what we predetermine. The idea being we don't want to exceed the margin of error. That's the idea. That's our threshold, our limit. We don't want to exceed the margin of error. We want it within a margin of error. And the margin of error is computed as the z star times p, and I put a star on it depending on what information you have, 1 minus p over n with a square root around it. So how does the n behave here, where we drew the formula from? If n is higher, then the margin goes down. So if we want to maintain the margin of error at we don't want it to exceed a certain amount. In this case, 1%. Well, we said a width of. It was a width of. Let me go back. I have to remember. So the m here was that we used was 1, right? So for a margin of 1%, we don't want to exceed that. If we round down, because this is closer, or we use the natural kind of rounding at 5 or something like that in our thinking, then we would have the wrong answer. This would be too small if this was small, so I'll reverse what I just said. So let's say this was small. This is smaller. Then what happens to the margin of error? It gets larger, you see? So we actually we choose to round all the way up. So this is a rule. This is the only time you're going to round this way that I mentioned in this class. Maybe there's other reasons to round this way. But this is when you will round all the way up to maintain your margin small. Okay, to make it be less than 1%. That's the logic. Any questions about that? You hear my neighbors? Hope not. They have a son, and he's very excited. All right. Let's see now. Okay, back to the formula sheet. So what have we done? We've tackled now, recapping what we've done so far. We've analyzed, we've understood now, this is for the C% confidence interval, this is the formula. This is the formula for sample size estimation, and now we're here. What is this? This is known as test of hypothesis. I won't be able to write it nicely. I have to make it bigger. This is test of hypothesis. We are now coming full circle from the first unit where we discussed designing experiments, and now with a sample, we talked about sampling. With information about a sample, we can test hypothesis. That's what this is all about. Okay, so we've come full circle now. Once I teach this, you'll feel you've pretty much learned the main topics of the course. I'm just going to repeat this row, confidence intervals, sample size estimation, and tests of hypothesis for, like this was all for the sample proportion. Then we're going to do this for the sample mean. So different statistics. Okay, so let's look at this. What are we staring at here? What is this? What do you see here? See a p hat, that's the sample proportion. I see this, p with a 0. This is a p with a 0. There's this, looks familiar, right? So what you should be thinking about, let's go back. Everything is on this sheet. In fact, let's go back and see, what is this all about? Now, remembering that I mentioned to you that in this row, we're conducting inference. This is a row for inference, guessing, educated guessing on the population proportion. And throughout, we never have p. P is unknown. So instead, we use a sample for p hat. Instead, if we don't have an old sample to figure out the sample size for a new sample we're going to draw, we just use 0.5 for this formula. That's what p star is. And then here we have a p0. So we don't have p, but we have p naught, p with a 0 on it, as a subscript. This is known as the null hypothesis. Okay, this is this is your hypothesized p. This is what you think it should be, and then the idea, the scientific method, requires us to disprove it with the evidence that we've accumulated, that we've collected. All right, so that's the approach. So what is this all about? This is remembering now, let's go up a bit. What was it that we learned about p hat? We learned, everything's on this sheet, I'm telling you. We learned that if we have a count variable that's binomially distributed, that means the sample is drawn such that each time we sample, the chance of getting something we're looking for doesn't change from observation to observation. Okay, that's basically what's happening there. Then we compute not just the count of how many successes we had, we can calculate the proportion of successes in the sample. And it turns out that that sample proportion, from the rules of means and variances learned in Unit 4, from there we know that the p hat has a mean of p and a standard deviation p1 minus p over n square root. If you want to review that, go back. And in Unit 5, I explain using the rules of means and variances, and I derive those. Now, what's next? So we know it's mean, we know what to expect, and we know it's variation, because it's not always going to be exactly that. In a sample, p hat is not always going to be the true proportion. There is some variation. It turns out that provided that the relationship between n and p is such that the mean is of x is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then it's true for large population. In other words, when the sample size times 10 is exceeded by the population size. When you have these conditions, and you won't have to check these. At some point, you just, if I ask you directly, you'll check it. But, yeah, you should check them when you're starting the problems. But usually I'll just say large, and that'll take care of that for you. All right? So these are the conditions to make this true, and make it true that x is approximately normally distributed. So also p hat is approximately normally distributed with p 1 minus p over n square root. That's what that says. So these are the mean and the variance of p. So this is from SDS. Remember, this was from SDS. This is what we learned. SDS for p hat. So when you see the symbols, p 1 minus p over n square root, that's the standard deviation. Now, did we just see that below? Yes, we did. Below, you see it here. What you see here is a z. Z means it's a standard, it's a measure of the standard deviations from the mean. So this is the point estimate, this is the estimated proportion from the sample. This is its mean from the theory, if you hypothesize a mean exists, because right now we don't know the population proportion. That's why we're trying to estimate it from a sample. So this is the hypothesized mean. And then this below, well, I guess I have to get the whole thing, is the standard deviation or standard error. Well, we can call it standard deviation or standard error. It's like a standard deviation, right? I can remember standard error is the word I use when I put p hat in there. But in general, that's what we end up calling this when it's the standard deviation of a estimator. So these are the hypothesized. That's what the 0 means down there. So what is a hypothesis? That's what we're going to talk about next. So before I get there, I just want you to confirm you understand. This is a Z statistic. It's a standardized statistic. You've taken the statistic that you got from your sample, dividing the number of successes out of n tries, and then you're standardizing it to say, well, how far away in deviations from the mean, how far away was my result from what I expected? That's basically what you're doing. And I'll give you enough examples to go through that. We'll just do one today, probably. That's all we'll have time for. Okay, so I'm going to just make sure that you're not confused. This is the hypothesized mean. That's what the not is for. And the hypothesized standard error. Okay? So now let's set up a problem. I'm going to jump from here. Just remember, this is just a standardized statistic. Let's look at a problem, and I will take you through the steps of conducting hypothesis testing. This is essentially the rest of the course, okay? It's going to be confidence intervals and sample size estimation and hypothesis testing. This is what we're going to do for the next 2 weeks, okay? So if you get it now with just the slight variations for different statistics, you're going to be doing great. You're going to be great. If you don't get it right now, there's lots of opportunity to get it. Okay, I'm going to just save this. And then let's take up a problem. And I hope you can appreciate the importance of this. This is everything we've learned, everything we've done was to culminate in our ability to conduct tests. I mean, prepare to collect samples and then analyze the samples. Essentially, that's what we're doing. So here's my first test. It says example 3 because it's the third in the series, in the row. It's the third column of fourth set of formulas on the formula sheet. Okay, so a random sample of 900 individuals has been selected from a large population. It was found that 180 are regular vitamin users. Test the suspicion that less than 25% of people use vitamins. Okay, so what the approach we're going to take, I think I developed this, I don't know, but anyway, I hope you like it. It's the HAP-C method. Not happy, but HAP-C, because in the end we have a conclusion. That's what the C stands for. So I'll take you through the steps that begin with the hypothesis. The null and the alternative hypothesis. You always will write this. No matter what kind of hypothesis, you're always going to set up the problem with your parameters. In this case, I'm going to use P, an equal sign here. Whatever number I put here that the true proportion is, I also carry it down here. And then I have to talk about with you, the possibilities are that P is greater, P is less, or P is not equal to, okay? Okay, so what's a null hypothesis? This is known as the status quo belief, the status quo. What is status quo? It's what everybody knows to be true, either from the past or some beliefs. So people have a sense, people have always assumed certain things. In this case, when you read this problem, there's not a lot of data points here. There's not a lot of pieces of information here. But this is what it looks like I'm testing against, the 25%. So what am I going to do with that? Well, I can't do much, except because the way this is set up, this has to be a statement of equality. Okay, so the null hypothesis has to be a statement. Anyway, the way that we're going to do this is a statement of validity, quality, exactness. Okay, it's not like these alternatives are the greater or less than. No, it's just one exact value. So the number I see is 25%. I'm going to put it in here. And because I've put it in there, I have to also put it here. And let me explain what we've just done. What I'm saying is, we currently believe that 25% of people use vitamins. That's the status quo. What we're going to do is collect a sample, and from that sample, compute the sample proportion of people who use vitamins, and that should be close to 25%. It should be, knowing that sample proportions have some variation. It's not going to be exactly the true population proportion, but it shouldn't be an outlier, right? It shouldn't be like more than 3 standard deviations from the mean. It should be close. So what we're going to do is we're going to say this is the status quo. We should expect in any sample that we get 25% as vitamin users. But if we find evidence that that's not true, in this problem, they specify that we want to test to see if less than 25% of people use vitamins. Okay, so I translate that into that symbol out of the 3 possibilities. Okay, that's the one I'm going to use. So I have to see that my sample proportion is different enough from 25% in terms of being an outlier, too many standard deviations away, that's going to make me reject the null hypothesis or the status quo. And when we reject the status quo, we look at the next best thing is to believe the alternative. This is the alternative hypothesis. So this is the alternative, that's what A stands for. And this is called the null. And that's what you believe to be true. If we find evidence against the null. Okay, so we find evidence against the null. We reject the null. I'm going to explain all of that in a bit. And we believe this to be true, that it's less. All right, so that's how we determine what those are. So that we've completed now the hypothesis statement. This is the statement. So in any problem of testing, you have to begin with the statement of the null and the alternative. Now these here, this is actually the P naught. Okay? That's the hypothesized P. All right, so we've covered that. So given this statement here, we have been given information on the results of a sample. So what do we have? We have 900 individuals had been selected. So that represents N is 900, right? And then we find that 180 use vitamins. So that means X, the number of successes, is 180. We have N, we have X. So from there we can calculate P hat. So this is how I use the information. I'm not giving myself enough room. Let's do this way. So P hat is equal to X over N which is 180 over 900. So I hope you're making these calculations as we go so you can stay awake while I'm doing this. And what do you get when you take 180 divided by 900? You get 20%. You get 0.2. Aha. Okay, so we get 20%. 20%. Let's see that. Let's take that in perspective. 20%. 20% We got 20%. We were expecting the status quo of 25, but we just got 20. So did we find something lower than 25%? Looks like it, but we got to test it. We have to verify that the 20% is significantly lower. Okay, so this is what we're getting into. This is statistics. Is it significantly lower in statistical terms, given the assumptions we've made? What assumptions are we making? We are making assumptions to do this. That's what A stands for. We need to assume something. We can't do anything with the information we've given unless we stick our neck out and make a hypothesis. We believe, right, that the status quo, or we're going to test and say, well, the status quo believes that 25% of people use vitamins, so we're going to assume it's true. Otherwise, we can't even begin to test. So we're going to assume H0 is true. What does that mean? It means that P, the true proportion, is equal to the 25%. It's equal to P0, which is 25%. Okay, so this is what we believe to be true. Now, what are the implications of that? Believing that to be true means that then the sample proportion from which we computed for one sample that it was 20%, it's actually approximately normally distributed with a mean of P and a standard deviation P times 1 minus P over N square root. Okay, so I'm going to hypothesize that it's going to be 25%, so I put that in there and I compute now the standard deviation for that 25%. To do this, remember this is from formulas in number 2 of the formula sheet that I can do this, and this is providing that the sample size is large, which I assume, and that N times P, so that's 900 times 25% is greater than 10, and then 900 times 75 is greater than 10. They are, so this is true. Those are the conditions, so it's true. So let's see, I'm gonna just summarize. So P hat is approximately normal with a mean of 25%. I'll use decimals. And then this, we have to calculate this. Let's just do this on the side. And then I'll put it in so it looks nice, neat. P 1 minus P over N square root is 0.25 times 0.75. Remember, I don't use the formula. I don't like repeat and plug things into the formula. I just put in the complement right away. Divided by N is 900, and square root. That's what we're computing. Punch that in. Punch that in, and it's equal to 0.0144. Okay, So that's where I got that from. I'm going to plop it in to here. And I'm rounding to 4 decimal places. Whenever you work with the p's, with the sample proportion or proportions, or binomial problems, round to 4 decimal places. So there it is. That's the assumed step. Okay, so this is what I've assumed, that H naught is true, so the status quo holds, so it must be true that the sample proportion is distributed approximately normal with that mean, the true proportion, and there's, as a consequence, this standard deviation. So this standard deviation is very small, so it means that the values to be like 25% need to be near 25%. Let's see if we can test that next. The next step for the A is, it's called assess. The assess step. What are we assessing? We assess the evidence. What is the evidence? No, the question has it's a very short, I think it's, 2 sentences question. It has lots of information. Assess the evidence. What's the evidence? The evidence of the sample. P hat was equal to x over n, which was 20%. We calculated that above. It's 20%. So we're going to assess this. We're going to determine how many standard deviations that is away from what we expected. So we need to compute the z. Z is your p hat minus your mean divided by your standard error or standard deviation. Okay? So we know those. We just computed them. So don't forget where you're going with this. There, here, right here. So I can do this. I can standardize 0.2. 0.2 minus 0.25 divided by 0.0144. What do you get? No square roots, nothing. We already did all the calculations. All we have to do is standardize. So now you see the importance of unit 2 normal, right? You see everything we learned was to do this, to lead us here. So it's a negative. It is a negative. It is lower, right? It's lower, so it's going to be negative 3.47. So for us, that's an outlier, right? This is 3.5 standard deviations below the mean. So we already know the answer. The answer is that, yes, we do have evidence to reject the null. The question is it significant? Well, it is. I know it is going to be, but let's put it in terms. Let's run through the remaining steps in a systematic way. This is how you attest to the fact that you should reject the null hypothesis given this evidence. Okay, so we are far away. We're in an outlier. It's just a matter of is that far enough? And and how are we going to phrase that? So this is what we're going to do. I'm going to do the next step. So the next step is P. This is called the p-value step. P-value. What is a p-value? The p-value step is the probability of seeing a result, or we'll put it in the terms of the problem, I'll just say it like this, a Z stat, right? So Z statistic as extreme or more extreme if you don't understand what I'm talking about, that's fine. I'm going to clarify all of this. Given that H naught is true. So the p-value is a computation of the probability of seeing a Z statistic as extreme or more extreme given H naught is true. What the heck am I talking about? What's a Z statistic? Okay, let's go back. What you computed above in the assess step was a Z score. Because you used the sample result to find the p hat, and then you standardized it, the Z score, this Z is a statistic, right? What else is a statistic here? Remember, a statistic is a number computed from a sample. This is a statistic. What else is a statistic? P hat is a statistic. It's a number calculated from the sample. We have to distinguish between statistics and parameters to not get mixed up. Okay, so that's a statistic. You made a computation using the statistics results, the results of the sample, and use the statistic to get this statistic, okay? And what we're doing is we're saying, what's the chance of seeing this Z? So I'm going to convert from number of standard deviations from the mean to probabilities. That's what the p-value does. So this p hat that we got in this sample was one of many that we could have got. I'm going to draw it. You got to draw this. If you don't want to draw it, you should, because you're going to explain to me how you got your answer. This is not very clear. Here's it. What is this line here? Hold on. Okay, so this is what we're looking at. We draw the Z, the standard normal curve, and we put our Z stat on it. Our Z stat in this case was negative 3.47. And we want to look, like it says, seeing a Z statistic as extreme or more extreme given H naught is true. So my calculations were already taking into account that H naught was true. In other words, we assumed P was 25% to derive its the mean and standard deviation of the sample result. Otherwise, we couldn't have done anything. But so that's already taken care of. What's concerning us now is, what does extreme or more extreme mean? In other words, which way do I put the arrow? That's all. When was the last time we saw an arrow? We saw an arrow when we made the statement way up here this is finally where we use this alternative hypothesis. The alternative hypothesis is not used until the p-value step, okay? You put it here and then you use it in the p-value step. And this says we're going to test to see the chance of having something less, having something lower than we got. So we use the less than from the alternative hypothesis to test that. So what's the probability of being out here? Oh, you can't see it, can you? Hold on. There you go. What's the probability of being as extreme, so negative 3.47 standard deviations below the mean, or more extreme than that? That's the probability. This is called the p-value. Okay, so the p-value is you can put it in words, you can make it an image, you don't have to write all those words out every time. All you have to do is show me that you're computing the probability. Given the null hypothesis, all this is only possible because we made a null hypothesis that we knew the proportion. So what is that going to be? Get your z table. If you look it up in your z table, you get the number 0.003. So the p-value is very small. So what it means is the chance, the probability of seeing that value that we got 3.5 standard deviations below the mean was very unlikely. The chance was very small. It was so small. It was 0.03% chance. You don't want to operate with a 0.3% chance of anything good, but for bad things, that's a nice probability, right? You don't want. It's a small number. So what do we do with that? The last step, let's conclude. What does it mean? How do we wrap this up? I want to erase that. Okay, so the concluding step, C for conclusion. We know that it's bizarre. It's very unlikely that we would get 20% when everyone believes that it should be 25% of people using vitamins. We found statistically, given the assumptions, we found statistically that in fact, it's almost impossible. It's very unlikely that we would have gotten that result. So we are going to have to make a decision. Either something's wrong with the evidence or something's wrong with the assumption. We have to make the additional assumption now that nothing's wrong with your evidence. The sample was collected properly. There were no measurement errors. We're going to assume the sample was properly corrected and the calculations were done properly. The data was recorded properly. All these things. No measurement errors, no no bias, okay? And we're going to instead reject H naught. So we're going to reject the null hypothesis. How do we write that up? So for the concluding step, we always use this format. P-value less than or equal to alpha means reject H naught, reject the null hypothesis. That's what it means. Okay, so what is this? So p-value, we have that. Alpha, so we have to ask ourselves, is 3%, I mean, it looks really small, but who's to say that's a real small chance? So we have to have some sort of threshold. In statistics or in research, it's often the case that it's set at 5%. So we say anything unusual would be considered unusual because it's unlikely, it's less likely than 5% of occurring, and it did occur. So we're going to use 5%. This is known as this alpha is the level of significance, and we'll talk more about that tomorrow. I'm not going to be able to fit that in. Okay, so that's the level of significance. And we assess, let's assess this. So is it true? Is this statement, so I take this statement, like I said, no matter if it's a left-hand side, a left alternative hypothesis or a right, higher alternative hypothesis, it's always the statement that you make, and you test the statement. Is it true? Yes, this is true. So we do reject the null hypothesis. What do we conclude in words? So when I want you to make a conclusion, I'm asking you to test, make a statement about the p-value being less than the 5%, unless I tell you to use a different level of significance. It's less than 5%. We reject the null hypothesis, and we conclude that there is evidence to support that less than 25% of people use vitamins. That is a concluding statement. That is a complete answer. All right? Let me write that up. First, we say the test is significant. That's the main thing. And then you elaborate. There is evidence that less than 25% of people use vitamins. Now notice I talked about the 25. I didn't say the 20. The 20 was just one sample. Okay, this one sample, but it was enough to make the statement that we have evidence. Okay, this is substantiated using statistics. It's statistically significant result, and we refer not to the 20%. We could report the 20%, but when we make our concluding statement, all we've shown is that there's evidence that less than 25% of people use vitamins. Remember that 25% was used to make all of our calculations once we made the assumption that it was true. So that's all I know. I don't know that it's 20% in reality. That should be a better mean. I just know that I found evidence that it's less than 25%. If you guys don't have any questions, I'm going to stop there. The quiz is going to open at 6 o'clock. And I'm going to, I still have to post the makeup quizzes. So work with the current quiz and I will post those makeup quizzes. I apologize for not marking everything, but I can't even begin to tell you how much work I have to do, how many things are going on. But I will mark everything and I will post all your grades and in time so that you can dispute them if I made a mistake. All right? So don't worry about that. Once the final exam table comes out, we'll know when the final test is. I can continue streaming if you can send me problems like we did for the midterm. We'll do the same for the final. There's a ton of finals. Well, not a ton of finals, but I put finals up and I put some review problems up for you so we can work through those. And I also gave you an exam distribution so you can see the most of the exam final will be on Unit 6. Everything else was to support our understanding of Unit 6 and our success in Unit 6 and proceeding through it and testing you in it, okay? So you need everything that led up to 6, but that's where I'm going to conduct 40% of the testing. In other words, 40% of the questions will be based on inference. So have a good night, and we will talk tomorrow. Bye.